Hi everyone! Today we're going to be talking about inductive reasoning, conjecture, and counterexamples. Our objectives for today are that students will be able to make conjectures based on inductive reasoning, and you will be able to find counterexamples. Let's get started. You may ask, when am I ever going to use inductive reasoning? Well, here's a real-world example. Market research is conducted by an analyst to answer specific questions about products that we use on a daily basis. For example, a company that creates video games might hire a focus group of testers to play an unreleased video game. The process of using patterns to analyze the effectiveness of a product involves inductive reasoning. Alright, so let's write down a couple definitions. So inductive reasoning. What is inductive reasoning? Inductive reasoning is making a conclusion based on observations and patterns. So inductive reasoning is making a conclusion based on observations and patterns. A conjecture. A conjecture is a concluding statement reached using inductive reasoning. So after we use inductive reasoning, we've made a conclusion based on our observations and patterns, we write a conjecture, which is a statement summarizing that conclusion that we've reached. Alright, if you need more time to copy down these definitions, go ahead and pause your video. Otherwise, let's move on to some examples. Alright, so our examples. We want to find the next 5 terms of the sequences and then write a conjecture. So we want to use our observations, look for patterns, make a conclusion, and then write a conjecture or a concluding statement describing the conclusion we've made. So for number 1, we see that we go from 38 to 31 to 24 to 17. We're looking for a pattern here, and we see that we're subtracting 7 to get the next term, right? 38 minus 7 is going to give us 31. 31 minus 7 is going to give us 24. 24 minus 7 is going to give us 17. So in order to find the next 5 terms, we want to keep subtracting 10. So subtracting 7. 17 minus 7 gives us 10. 10 minus 7 gives us 3. 3 minus 7 gives us negative 4. Negative 4 minus 7 gives us negative 11. Negative 11 minus 7 gives us negative 18. Alright, now we want to write a conjecture, so a statement, a concluding statement that we've reached based on the observations and patterns that we've seen here. So I'm going to type this out because my handwriting on here is never neat. Alright, so hopefully this works. Alright, let's see if we can move this up so it's in line with the line. Oh well. Alright, so our conjecture that we're going to make is we're going to say to generate, there we go. Let's fix this. To generate the next term, subtract 7 from the previous term. Alright, so that is our conjecture. In order to generate the next term, subtract 7 from the previous term. And you're done. Alright, so number 3, our terms are 1, 4, 9, 16. We want the next 5 terms. So if we're looking for a pattern here, we see that to go from 1 to 4, we add 3. To go from 4 to 9, we add 5. Then we add 7. Alright, that's sort of a pattern, but not really. Alright, another thing right off the bat that we can notice is that all of these numbers are perfect squares. 1 squared gives you 1. 2 squared gives you 4. 3 squared gives you 9. 4 squared gives you 16. So the next term is probably 5 squared. That's going to give us 25. And then we're adding 9. So we add 1, add 3, or add 3, add 5, add 7, add 9. Alright, then 6 squared gives us 36. 7 squared gives you 49. 8 squared gives you 64. 9 squared gives you 81. So our next 5 terms are 25, 36, 49, 64, 81. And this is a much easier pattern to describe than, say, we're adding 3, then adding 5, then adding 7, then adding 9, all right, then adding 11. Well, you could describe that pattern saying that they're all perfect squares is much easier. So the conjecture that we would write for this is we would say each term is a perfect square. All right, let's move that up on the line. So each term is a perfect square. To find the nth term, or the next term, right, we would square n. So if the first term, or the nth term, is 1, right, if we're saying the first term is 1, we square 1. The second term, the nth term, is 2, square 2. If n is 3, that's the third term, square 3 to get the third term. If n is 4, that's the fourth term, square 4. If n is 5, that's the fifth term, or the nth term, square 5. If n is 6, square 6, and so on and so on. So that is a conjecture we can write to describe this pattern. Alright, so I want you to try number 5 on your own. Try to find the next 5 terms in the sequence and then write a conjecture to describe the pattern that you used to get the next 5 terms. Write a concluding statement or a conjecture. When you come back, I'll have the answer written on your screen and we'll go through it together. Alright, so you should have gotten the next 5 terms being 8:45, 9:10, 9:35, 10, and 10:25. So if we looked for a pattern here, we saw that we were adding 25 minutes to get the next term, and we're dealing with time here. Alright, so if we add 25 minutes, add 25 minutes, add 25 minutes, and so on. Alright, so to generate the next term, add 25 minutes to the previous term. This is a conjecture that's describing our pattern and just making a concluding statement using the inductive reasoning that we used to come up with the next 5 terms. Alright, if you have any questions, please call me over, raise your hand so I can help you. Otherwise, let's move on. Alright, so a counterexample. What is a counterexample? A counterexample is an example that, let's see, I didn't spell example right. Oh, I did. Example that shows that a conjecture is false. So a counterexample is an example that shows that a conjecture is false. Let's see some examples where we need to use a counterexample. Alright, so some problems where we will need to use or provide a counterexample. We want to determine whether the conjecture or the concluding statement is true or false. If we think it's false, we have to provide a counterexample. So we have to prove it false. So number 1, the sum of any 2 consecutive integers is always odd. So first thing, let's break down the wording of this problem. So the sum means when we add them together, right? Sum means adding. And 2 consecutive integers. Consecutive integers mean numbers that come right after each other. So like 3, 4, 5. Those would be consecutive integers. They come one right after each other. If we add any 2 consecutive integers, it's always odd. So what we want to do is test this out. Let's start with the consecutive integers that we have here. So 3 plus 4 equals 7. 4 plus 5 equals 9. Let's see, 5 plus 6 is always going to equal 11. Anytime we add an even and an odd number together, it's always going to equal an odd number. Alright? So we could do this until we're blue in the face a million times over, but this is a true statement. Anytime we add together 2 consecutive integers, it will always be odd. So therefore, this is a true statement. A true conjecture. And we're done. All right, number 3. The product of two perfect squares is always a perfect square. So first, let's dissect the wording of this problem. So product means we're going to multiply. And we've got two of any two perfect squares. So perfect squares would be 1 squared gives you 1, 2 squared gives you 4, 3 squared gives you 9, and then 4 squared gives you 16, 5 squared gives you 25. All right, these are all perfect squares. We're saying if we multiply these together, it's always going to equal a perfect square. So let's test it out. Let's start with what we have here. 1 times 4 equals 4. All right, perfect square times perfect square equals perfect square. 4 times 9 equals 36. 36 is a perfect square. 6 squared gives you 36. How about 4 times 5? That's an easy one times 25. That's an easy one we can do in our head. We know that's 100. All right, so that gives us 100 is a perfect square. 10 squared gives us 100. Let's try 9 times 16. Plug that into our calculators. Let's see, 9 times 16 gives us 144. 144 is a perfect square as well. All right, 12 squared gives us 144. So we keep trying all these, and we can't think of anything that proves this to be false. All right, if we could come up with an example that proves this statement false, that would be a counterexample. But we can't come up with a counterexample, so we say that this is a true statement. All right, and we're done. All right, number 5. Dividing by 2 always produces a number less than the original number. If we're thinking about this, all right, if we're dividing by 2, so if we have, let's say 10, and we're dividing by 2, that does equal a smaller number. That equals 5. All right, so that is not a counterexample because that proves it to be true, right? What we want to think of is we want to think of something that proves this false. That would be a counterexample. Now, what if we divided a negative number by 2? What if we said -8, that's our original number, and we divide that by 2? We end up with -4. Now, -4 is bigger than -8. So this counterexample, we're going to call this a counterexample because this example right here proves this statement false. All right, because dividing by 2 doesn't always produce a number less than the original number because -4 is bigger than -8. So this is false, and we have to provide this counterexample. We have to provide a counterexample that proves it false. So if it's true, you don't have to provide an example, all right? But if it's false, you always have to prove it to be false with a counterexample. All right, number 7, I want you to try on your own. All right, determine whether this conjecture is true or false. If it's false, make sure you provide a counterexample. All right, when you come back, I'll have the answer written on your screen, and we will go through it together. All right, so number 7 is true, all right, because anytime we're multiplying two numbers together, one of the numbers has to equal 0 if our product is 0, all right? If we're multiplying two numbers together and it equals 0, either the first number or the second number has to equal 0. So this is a true statement, all right? I don't know about you, but I can't think of any time where I'm multiplying something together and one of them isn't 0, but our answer is 0, all right? Doesn't happen. So this is a true statement. All right, I want you to try number 9 as well. All right, determine if this conjecture is true or false. If it's false, provide a counterexample. So all state names have at least 2 syllables. Either say this is a true statement or say it's false and provide a counterexample. When you come back, I'll have the answer written on your screen. So pause your video now. All right, so this one made you think a little bit, right? You had to think back on all your state names. So the answer is false. I came up with the counterexample of Maine. Maine is a state with a single syllable. It has one syllable, Maine. All right. If you guys thought of any other states with a single syllable, let me know. All right, that was the only one I could think of at the moment. But this is false because Maine only has one syllable. All right, so for numbers 11 and 12, what I want you to do is write 2 conjectures of your own. All right, they can be about anything. They don't have to be about math. They can be about something that interests you, something that you and a friend have in common. All right, anything you want. If you want to write them about math, awesome, but they don't have to be. All right, so write 2 conjectures, and then when you're done, look for somebody at your pod or nearby who is also done and that you can trade with. Determine if their conjectures are true or false, and if they're false, provide a counterexample. Then trade back and check what your neighbor or your friend did and see if they're right, because you are the one who created these conjectures, so you know the right answers. All right, just a little bit of practice and you can do something that interests you. It doesn't have to be about math. All right, so once you've done this, trade with a partner, see what you guys get, and then after that you are done with the video notes for today. So when you're done with that, look to the board to see what to do next, and then call me over to stamp your notes, and I hope that you have a great day.